Hello everyone, welcome to lecture number 58 in this NPTEL course on Riemannian geometry. So we are in the process of proving the uniformization theorem. So there are two key ingredients which we covered in the previous two lectures. So let us say Mg is a space form with sectional curvature identically kappa. Then the first main ingredient was that in geodesic normal coordinates one can write a polar coordinate expansion of the metric. As a consequence of that, in this geodesic normal neighborhood or this geodesic normal neighborhood is actually then isometric to some neighborhood in the model space. So here we already get some sort of local isometry of the space form with the model space. The second key ingredient was the generalization of this no conjugate point result. So let us say I have a geodesic gamma which is unit speed. Then if kappa is non-negative, then in fact there are no conjugate points at all, and if kappa is positive, then the first conjugate point lies beyond a distance of pi by root k. Okay, these were basically consequences of the Jacobi field comparison principle. Alright, so now I am going to use these two to actually complete the proof of the uniformization theorem. So let me remind you of the statement. So let Mg be a simply connected space form with sectional curvature identically kappa. Then the claim is that Mg is isometric to M kappa G kappa, to the corresponding model space. Okay, so let me we have already sort of done enough to quickly give a proof in the non-positive case. So let me quickly give you a proof when kappa is non-positive. So in this case, because the sectional curvature is non-positive, the Carta-Hadamard theorem applies. So Carta-Hadamard implies that the exponential map is a diffeo, because M is simply connected, right. So then this is a diffeo. So in other words, we have geodesic normal coordinates on all of M, right. So now you can apply the first ingredient. So ingredient 1 will imply that because now we have geodesic normal coordinates on all of M, and M is isomorphic to is diffeomorphic to Rn. So then one can use the first ingredient to explicitly write down the metric in polar coordinates, but that is exactly identical to the metric of the model space in polar coordinates, right. So that shows that this has to be isometric to the model space, and we are done, right. Okay, so all that now remains is when kappa is positive. Okay. So for this we'll actually need the following lemma. Okay, so let UG and VH be arbitrary Riemannian manifolds, they need not even be complete. Okay, and suppose I have two local isometries phi and psi, such that for some point P phi and psi agree at P and their derivatives also agree at P. Okay. So then phi and psi have to be the same. Okay. So that's the claim. Okay. What is the proof of that? So let's consider the set S. This is the set of all x in U such that it satisfies these two conditions, that is phi of x is equal to phi of is equal to psi of x, and the derivative at x is identical to the derivative of psi at x. Okay. So then clearly P belongs to S, so S is non-empty. Also clearly S is closed, right, because phi and its derivative, they are all continuous maps. So clearly S is a closed set. My claim now is that S is open. Okay, assuming this, we are done, because U is connected. So assuming this, since U is connected, this implies that S will have to be all of U. Okay. In particular, this will imply that phi is identically equal to psi on all of U, right. Okay, so how do you prove the claim? So let Q be a point in S and UP epsilon be a geodesic ball, right. So that means we have normal coordinates on UP epsilon. Okay, then for all x in Q epsilon, U Q epsilon. Then for all x in U Q epsilon, there exists a tangent vector of norm less than epsilon such that x is equal to the exponential of Q of V. Okay. So then we consider the following geodesic: gamma of t is exponential of Q of TV. Okay, and let sigma be equal to phi composed with gamma, and omega be equal to phi be equal to psi composed with gamma. Okay. Then these are geodesics from phi of Q, which I will denote by Q prime, but that is also equal to psi of Q. Why? Because Q is a point in S, right. So phi of Q is equal to psi of Q. So I will call that point as Q prime. Okay. From this point to phi of x and psi of x respectively. Okay. So my subclaim is that in fact phi of x is also equal to psi of x. Okay, what is the proof of this? Well, since Q belongs to the set S, I know that this derivative map is also identically equal to the derivative map of psi, right. So now let us compute the velocity vectors of sigma and omega. So sigma prime at 0 by the chain rule is precisely given by this. Okay. So that is this applied to V, but this is the same as d psi applied to V, but by the same application of chain rule, this is omega prime at 0. So that means sigma and omega are geodesics with the same initial point and the same initial velocity vector. This implies that sigma is identically equal to omega. In particular, sigma of 1 is equal to omega of 1. Okay, so we are done. Okay, but just take a step back and see what we have done. So what we have shown that for all x in this geodesic neighborhood, phi agrees with psi, okay, but up epsilon is an open set, right? It's a geodesic ball, it's an open set. So if a function, if two functions agree on an open set, then their derivatives on that open set also agree. So this implies that this is identically equal to d psi for all x in this, which means that this entire geodesic neighborhood is contained inside S, but since Q was arbitrary, this should be, this is a typo, these are geodesic neighborhoods of Q, okay. So this implies that S is open, and hence the claim is proved, and hence the lemma. Okay, so now I am going to use this to give a proof of the uniformization theorem for positive kappa. Okay, right. So the situation is as follows. So you consider a sphere, and let us look at the tangent space at the north pole. Then we know that there is a ball in the tangent space of radius pi, so that the exponential map is actually a diffeomorphism. Okay. On the other side, we have our arbitrary space form, simply connected space form. Let us take a point P here. What I am doing is, without loss of generality, by scaling I am going to assume that kappa is actually equal to 1, right, so that I do not have to keep writing pi by square root of kappa and so on. So then by our no conjugate point theorem, we know that if you consider the ball of radius pi in the tangent space to M at P, then the exponential map here so maybe I will write a bit bigger. So in this case the exponential map is a local diffeo on the ball of radius pi around the origin. Okay. So on the one side in the sphere we have a genuine global diffeomorphism. On the right on M we actually have a local diffeomorphism. Of course this is due to the conjugate point comparison principle. Okay. So we are now using the second ingredient. Alright, so now we do the following. So let L, so in the picture I am going to take an isometry L between the two tangent spaces. That can always be done. They are finite dimensional vector spaces of the same dimension with an inner product, so you can take an isometry. So let L be an isometry. okay, and we consider the following. So H1 is going to be the exponential you consider the isometry L and then you move down by the exponential map at P, you pull back your metric G via this map, and H2 you do the same, but you take the exponential map at the north pole on the sphere, that is a diffeomorphism. So, you can take the inverse of that or rather sorry you just take the exponential map at the north pole and pull back the round metric on the sphere. So, both of these are actually metrics on the ball of radius pi in the tangent space to the sphere at the north pole. Okay. So, they are of course not in general they will not be complete metrics on this ball, but there are some Riemannian metrics, and of course it is easy to check that the sectional curvature of each of these will still be kappa, which we are assuming is 1, right. So, the sectional curvature is still 1. Okay. Because these are local isometries. Also an observation is that the radial lines are geodesics for these metrics. Okay, so here the argument is similar to the argument that we had in the proof of Karta-Hadamard, that the radial lines in the tangent space are geodesics. The same argument will also work here. So, I will let you ponder over that for a little bit, but the upshot is that this implies that the standard Euclidean coordinates on this ball are actually geodesic normal coordinates. Okay. Then by our ingredient 1, this implies that H1 has to be identically equal to H2, right, because on a geodesic normal neighborhood any metric is given in polar coordinates by that explicit formula. So, both H1 and H2 are given by that explicit formula. So, they have to be identically the same. So, now consider the following. So, now consider the following. We consider the map phi from Sn minus the south pole to M given by the following. So, phi, you take the exponential map at the north pole, that is a diffeomorphism from the ball of radius pi to Sn minus S. So, you can invert that map, you then compose it with this isometry to get something in the tangent space at M, and then compose it with the exponential map at P. Okay. So, clearly phi is a local diffeo. Okay. Because exponential map at P is also a local diffeomorphism, the other two maps are actually diffeomorphisms. So, now we pull back the metric. I want to actually claim that phi is a local isometry. Okay. So, let us pull back the metric G via phi. So, by definition that is going to be this. Okay. but this guy is precisely h1. So, this is exponential n inverse star of h1, but we have shown that h1 is identical to h2, but by definition what was h2? h2 was the pullback of the round metric on the sphere via the exponential map. So, this is precisely the round metric on the sphere. Okay, so this implies that phi is a local isometry. Okay, but now this sort of covers almost everything except it leaves out this the south pole, right, annoyingly. So we do the following now. So now let Q be a point that is not the north or the south pole, okay, and let little q be the image of capital Q under this local isometry. So now we repeat the same process, except instead of P and the north pole we do it with minus Q and the corresponding or sorry Q and the and this little q. So let L prime be an isometry, let L prime be given precisely by d phi at Q. Okay, so because phi is a local isometry, this is clearly an isometry between the tangent spaces. Okay. Yeah. So now repeat the same construction as before. So repeat the construction as before, with this L replaced by this L prime to obtain a local isometry psi, which will now be from Sn minus the point antipodal to Q. So Sn minus you remove minus Q to M, okay, where psi is now given by the exponential map at Q composed with L prime composed with this, right. So now one can check explicitly. So check that in fact phi at Q and psi at Q are both little q, and because L prime was given by the derivative of phi at Q, one can also easily check that d phi at Q is identically the same as d psi at Q. So then by the lemma, phi is identically the same as psi wherever they are defined. So on Sn minus Sq, okay, but then just then consider this phi tilde, which is equal to phi on Sn minus the south pole, and psi, or maybe I will use a different letter. So consider F and it is psi on Sn minus the point minus Q, okay. So then because of this observation, F is a global isometry. F is an isometry from F is a local isometry defined on all of Sn. Okay. But then by Ambrose's theorem you have a local isometry which is surjective. So you have a local isometry from Sn to M, So then by Ambrose's theorem, because Sn is obviously complete, this implies that F is a covering map. Okay, but then because M is assumed to be simply connected and Sn is simply connected, this implies that F has to be a diffuse by the uniqueness of universal covers, right. So this implies that F has to be a diffuse in other words, F is an isometry, is a global isometry. So that proves the uniformization theorem. Okay. All right. So that takes us almost to the end of the course. In the next lecture, I thought I will do something related to this theme of curvature and topology. So I will prove Meyer's diameter comparison result, which has some nice topological consequence for manifolds with positive Ricci curvature. And then in the final lecture, I thought maybe I will talk about a very beautiful theorem of Schur on constant sectional curvature matrix. Okay, so that should see us through to the end of the course. All right, thanks for your attention, and I will see you next time. Thank you.